In this question, we are being asked to go back to a prior problem where we're looking at the truss system with three members and calculating an axial stress or a normal stress in one of its members. So we're looking at trying to look at what the stress in cross section of member three might be. Now, let's review what this problem actually looks like. If we come down to our session number 2, okay, you'll find these slides in there, and we might have gone over them too quickly in class to really have had a chance to understand what's going on, but you can also review the material from statics to be able to understand this type of problem. So we have a simple truss, as you see here, and it has three members, 1, 2, and 3, and up here, this is a pinned constraint, so it doesn't allow this joint at this location A to be able to move up and down, but we have over here a point C which is on kind of a roller or sliding constraint that would allow it to move up and down, and then we have a load externally applied P at point B. So those are the three locations where we can draw vectors associated with external forces on the system. So you see here we have an AY and AX and a CX and a P. And in reality, we could choose for these constraints directions that we like. We don't have to follow a particular convention. But P was given to us going downward, so we probably should stick to that one. But for these other ones, we have some ability to choose. Now, as we know, when we do the method of joints, we first complete external equilibrium. Then we define a coordinate axis or system. We can apply Newton's second law with the forces and the moments. And in this case, we're going to be looking at the forces equal to 0, and we have at this location right here, AX going this way to the left and CX going to the right. So that is all that we're going to be looking at in terms of equilibrium in the X direction for the forces. For the Y direction, okay, we have a P going down and we have an AY going up. So we can say that we have AY equals P. And for the moments at, let's say, location C, so we can ignore the CX, we have, and then AY is going through the point, so that doesn't contribute a moment. We can say that we have an AX times this length L, and we have a PL, or P times this length L, and so that means that AX is going to be equal to P. In this problem, the given is P. That's what we know. Now, what should we do to solve for some of these unknowns in the members? Okay, because we've already done. So look, we have P here. We have AY, right? We have AX equals P, and we have AX equals CX. So this is a nice problem in the sense that at least the external forces on the system are now defined and understood. Okay, but we're interested in the forces within these truss members. Okay, so that means that we need to look at either using method of joints or method of sections to be able to figure out what's going on within the members. So for the equilibrium at the joints, or the method of joints, we're going to essentially uh, look at each one of the joints in the system, and for method of joints, we have to use all of them. Method of sections, which we won't cover here, doesn't give you the forces in all the members, but it allows you to kind of quickly only analyze the portion that's of concern for you. Okay, and just kind of restarting things here, one member, two member, three member, and our joints are going to be A, B, or A, uh, B, and C. Yes, so this point P is what we defined as B. So joint A, let's look at this first. we have our AY and our AX acting on the joint. Now, a little more confusing is what are the forces from these members acting on that joint? Now, if we draw the forces away, which actually we have a choice here. We could draw them the other way if we want. But if they're drawn away, that means that we are hypothesizing that if F1 and F3 in these cases would be positive, then these members would be in tension. Okay, and that may be a little bit counterintuitive, but if you think about it, this is a joint that has a force pulling it down potentially, okay, by this member 1 up here. So if it's being pulled, then on the other end of that member or some location of that member, I've got to have some type of force that's pulling and putting it under tension. So in general, if you have forces coming out of a node and those forces end up being positive, okay, the magnitude of F1 and F3, for example, are positive, then that means that the associated members that are along the directions of these forces, okay, those are going to be positive as well, and that's through equilibrium. Joint B, we will go ahead and draw the joint. And one thing in which we need to be consistent is that if we drew positive tension in member 3 this way, we also need to draw positive tension in member 3 for joint B. Okay, so that means it needs to be coming out of the node. Now, F2 coming in to this node means that at least if F2 were positive, then F2 or member 2 would be in compression. Okay, because it would have to be pushing in, and that would be causing it to be under compression. And P is the external load. For joint C, which is over here, we have to be consistent with F1. So we see that it's once again going to come out of the node. We have to be consistent with F2, all right, so it was coming in, so it's going to be coming in here. And CX is still using the same direction that we defined originally for the external equilibrium. So now we have the opportunity to perform more algebra and equilibrium at each one of these joints. So for joint A, we can write that we have AY minus F1 minus this square root of 2 over 2F3. Okay, so where does this square root of 2 over 2 come from? Well, this is looking at the contribution in the y direction, the vertical direction. So that means that we are only, okay, for these, for this equation, all right, we're only looking at the vertical direction. So AX, for example, is not in this equation because it has no vertical contribution. F1 is, and AY is, and 45 degrees of the F3 is. So if we think of a vector coming out, that's the hypotenuse. And so at 45 degrees, it's a 1 square root of 2. So it'll be 1 over square root of 2 times F3. So that's square root of 2 over 2 times F3 and is equal to 0. From our previous treatment of external equilibrium, we have AY equal P. So we can substitute P in here, and this is the equation that we get for the forces in the y direction. Looking down, this is then equilibrium in the x direction. So now AX is going to be, we'll say, in the negative because it's in the minus x direction. And we have a component in the x direction, once again, square root of 2 over 2 times the F3. Joint B, we can think of this equilibrium in the y direction again. So we have square root of 2 over 2 F3 coming this way. And that's going to be, there's going to be a positive component in the vertical direction. P is downward, so that's a negative component in that direction. Okay, and then this equation corresponds to equilibrium in the x direction. So we have F2, and then once again we have F3 contributing not only to the y direction like it was in this line up here, but also the x direction. So that's going to be square root of 2 over 2 F3 going the other direction. We come down to joint C, and we have F1 equals 0, All right, so you see that because there is no other component in the y direction. So f1's just got to be equal to 0. And we have cx positive and f2 minus. And so we now know that cx, or f2, is equal to cx. And we had previously calculated out cx as equal to ax, and ax is equal to p, right? So let's go a little bit further. This is just copying and pasting what you saw on the previous slide. We can solve for f3, okay? And we can use this equation right here to do that, because we have ax is equal to cx is equal to p, all right? Or ax is equal to p, sorry, right here, but cx is equal to p as well, all right? So we can solve for f3 using that relationship, and we can also do a combination of these three expressions to figure out what f2 is. So we've got f3 equals to square root of 2p, f2 equal to p, and we can also figure out what f1 might be, okay? And because we've got, well, let's just say here, right? So f1 is equal to 0, okay? Because that's what we calculated out earlier, sorry. So we've now solved for f1, f2, and f3. Now, you may say that's all well and good, and it is. Nonetheless, I just want to show you an approach to using linear algebra to be able to solve these types of systems of equations quickly. So here's equation 1, here's equation 2, and equation 3 that we've deemed to be useful for this problem. What you do is you stack them so that you have the f1, f2, and f3, all right? So imagine they're like x, y, and z or something like that, because we have three unknowns in these equations. And then we can look at this equation over here and say, okay, I'm going to use f1, f2, f3, but there's no f1, so I'm going to say 0 times f1. All right, just like there was no f2 in this one, so I'm going to do 0 times f2. And there's no f1 and there's no f3 in this last one. So I have a 0 times f1 plus f2 plus 0 times f3. So I have now this interesting looking set of equations that I could solve algebraically like we did on the previous slide, or I can create a matrix that describes the coefficients for the terms on the left. So you see 1, 0, square root of 2 over 2, 1, 0, square root of 2 over 2, 0, 1, minus square root of 2, 0, 1, minus square root of 2, 0, 1, 0, 0, 1, 0, all right? And then I can say, okay, f1, so f1 goes here, f2 goes here, and f3 goes there. So if I do my matrix multiplication, right, I have 1, 0, square root of 2, right, here, times this column. And the first element in this vector matrix right here, or this column matrix, or just this 1 by 3, no, 3 by 1, sorry, 3 rows by 1 column, is going to be equal to this p, like here. So this times this is going to be equal to p, which is what we have here. So I see pop, p0p, p0p, like that, right? And then in Python, I can solve for this f1, f2, and f3 by creating a matrix that you see here for this term, the A matrix we'd call it, creating a B matrix, which is the pop, and then the X matrix is what I'm solving for, so the f1, f2, f3. And when we do that, what we get are resulting values, okay, for this X matrix. So in this case, when we use p equal to 10, we get that the f1 is equal to 0, f2 is equal to 10, and f3 is equal to 14. And that makes sense because on the previous slide, we said f1 was equal to 0. We said f2 is equal to p, right? And p is equal to 10, so it's equal to 10. We said f3 is equal to square root of 2 over p, or square root of 2 times p, okay? And square root of 2 times 10 is going to be 14, right? Because square root of 2 would have been 1.41 approximately n times 10. All right, so that is how it's solved. Let's dive in, and if we look at the problem, it said there is code already available. So if we go now to the website, I guess I closed everything. So if we go to the website and we go to session 4 and we scroll down a little bit, there's the Colab that this problem instructs us to use. We open the Colab and we see that this should be saying session 4, not 3. Anyway, it says session 4. Anyway, whatever. I got distracted. But let's go ahead and run this first cell. So it loads the appropriate libraries. And in this problem, we need linear algebra and we need NumPy. Okay, so linear algebra can come from SciPy. And there's just a screenshot of the system in question. And now we have to fill in some blanks. Okay, so here it's asking for P and D, right? Because we're interested not just in the force, this question, right? So the example that from session 2 was on static equilibrium, so we were able to figure out the forces, but now we need to figure out the stress. So, and it's an axial stress because these bars in this truss, or these members of the truss, cannot handle anything. The only load they can handle is axial. All right, axial loading. So let's go back to the problem and plug in a couple numbers. We have here. Oh, you see, there's an answer already. Okay, well that's fine for the force. All right, and incomplete stress calculation, but 1808 and 1.2 centimeters. All right, so 1808. Oops, I went to the wrong place. So we'll put in 1808 and 1.2. Now, if you saw another example here, I've kind of violated one of my general helpfulness things of using centimeters here as units instead of just using meters. I'll show how to handle it sticking with centimeters, but some of you might just be like, I'm just going to put it in meters there. So I'll just you would multiply by 1/100th or 1e to the minus 2 to be able to, or 1e minus 2 to be able to get this into meters immediately. But I didn't do that. All right. Now, look, remember that this linalgebra.solve is going to give us a vector, okay, with 3 components. The 3 components being the F1, F2, and F3. Okay, so maybe that's not clear, but if we go back to, nope, well, that's fine. If we go back here, yeah, right? We were starting to solve for F2, F3, and F1, all right? F1, F2, F3. So that's an X vector that it's going to be, or X array if you want to think about it that way. That's what it's going to be giving us in Colab. So we're interested in member 3, and this may be something that throws people off. The arrays in Python are 0 index. If you've used MATLAB, they are 1 index. What does that mean? That means that the first element in an array or a vector or a matrix would be given by spot 1. In Python, the first element in an array is given by 0. So the 3 components of this array or this vector would be the 0th element, the first or the 1 element, okay, and a 2 element, 0, 1, 2. So if I'm interested in member 3, I don't put in x bracket 3, I put in x bracket 2. Okay, that might be a little bit counterintuitive. Now, we have fill in this line of code appropriately. So how do we fill it in? Well, we are going to say it's going to be the force divided by the cross-sectional area. So I don't put in P here, but I put in x2, because that will give me the force in member 3. Now, I already calculated it out by hand. And what did F3 equal? F3 was, if we go back, it was square root of 2 times the, right? It was square root of 2 times P. Square root of 2, where, right? We already calculated square root of 2 times P, okay? So again, this may be, an overkill use of Python to solve a problem, but I think it's good to see this process because you can use it to solve more complex trusses. So x2, and I need area, so the cross-sectional area. Now, what am I going to use for that? The diameter. Okay, and so what is the diameter, or what is the area for a circle? It's going to be pi d squared over 4. So I use mp dot pi. That's pi times the d squared. So this is a little tricky because I've got to take the d and I've got to multiply by 1e to the minus 2 to get it into meters, at least if I want my stress to be in pascals, okay? Then I've got to square it, so star star or asterisk asterisk 2, and then divided by 4, okay? And then I am hopefully closing things out appropriately. Yes, so this is pi d squared, okay, over 4, and it's all in the denominator. And then I'm going to say that the units here are pascals. So at this point, we just let it rip. We run, and it gives us a bunch of things. So remember this calculation here is just spitting. This is just a display of the X matrix. Okay. And no, sorry, it's a display of the A matrix, this first one, this 3 by 3. And then this array right here is a display of the X. So this corresponds to this 0th element is 0, which is F1. This one element, okay, which is corresponding to F2 is 1808, which is exactly what we put in. So that's a good sign. And we know it's supposed to be equal to the P. And then this third element is the second, or the 2 element, all right, and that was the square root of 2 times P, and yes, that is square root of 2 times P, and then I said print x2, so that's telling us just the force. You know, maybe if I wanted to be more careful, I would say, okay, print x2, you know, this is, I can say F3 is equal to this mp dot round, and I can go, where is the thing here, right? Okay, to this, like this, that's the first element. And I can even put it in newtons, just like that, okay? And so now it's a little more clear that F3, right? And so that's one of the beauties of, you know, using the print, so that you know what you're spitting out and you can keep checking units. Then we've got the stress calculation, and then this was converted to megapascals, so multiplied by 1 over a million, so 1e to the minus 6, and giving it to 2 decimal places. And that's the result. I hope you found this video helpful, and have a good day.